Hi, this is our walk of our project, uh, a model to predict the electrical energy output of a combined cycle power plant. I'm importing these libraries and loading our data over here, displaying the first few rows of the data set to understand its structure. And these are our features, and these are observations, and generating the summary to have a look on statistics of the data set. These are mean and minimum, maximum, and percentile values right here. And checking for duplicate row in the data set. After running the code, I found 41 rows, unless we delete the duplication patients. And as soon I run the duplicate, hopefully everything is gone. Confirm that all the duplicates are removed. I run the same command which I run over here. I run here. So the result output is 0. It means there is no more duplications. Otherwise, it creates noise and affect the model performance. Uh, Checking for missing values in the data set, running the code, and there is no missing values. The data is clean now. We may go ahead now. And calculating the correlation matrix for the data set. This is the summary over here. We can see there are some negative correlation, strong negative correlation, and there are some high positive correlation. Uh, this one may create multi-collinearity that affect the model's performance. We will check that later on. We talk about it later. And let's visualize the correlation matrix with the heat map. This is our code, and this is our heat map showing the same numbers in the heat map form. Strong negative correlation, uh, strong positive correlation, moderate correlation, minimal positive correlation, like this one. This is moderate, this is minimal. So let's we talk about it over here. Uh, Atmospheric temperature has a very strong negative correlation with PE, net hourly electric energy output, 0.95. This indicates that as temperature increase, energy output decreases significantly. Mathematically, these two values are inversely proportional to each other. Exhaust vacuum has a strong negative correlation, means higher vacuum value are associated with the lower energy output. Again, mathematically inversely proportional to each other. Ambient pressure shows a moderate positive correlation, 0.52, somewhat associated with high energy output. If AP is high, the energy output will be higher too. And RH indicates a smaller impact on the energy output compared to the other feature. Multicollinearity. This is where we talk about the temperature and vacuum strong correlation, which might indicate multicollinearity. This means that AT and V are highly correlated with each other. which can cause issue in model training and interpolation, and we take care of it later on. We will see that. And let's visualize the relationship between feature and target. This is our plot right over here. And let's visualize the relationship between feature pairwise. This is our graph over here, pair plot right here. And this is the 3 different levels: low in orange, medium in green, and blue in high is showing over here. Is actually the pair plot is right here. This is pair plot too, but in multicolors. I'm running the cross without cross validation and then cross validation. Let's see what happened. When I run without cross validations, this is the summary. Random forest is for sure is the winner. Second is the linear regression, and then decision tree. Let's do the prepare the data, define model, perform 5-fold cross validation for multiple models, linear regression, random forest, decision tree. When we run our model in 5-fold, this is our summary. Random forest is again winner. So these are the number over here. Because random forest mean MSE 19.12, lowest among the models, mean R squared 0.93, highest among the model. Conclusion, random forest is the best performing model, and we choose it as a final model. Let's do the build our model, because we already chose the best model out of 3. So hyperparameter tuning for the random forest regressor using grid search CV. We can do the random search CV too, because it's not a very big data, so we can go for grid search CV. If we have millions of observations, we might go for the random search CV. So these, after running it, we found, I'm not running because it takes long time, so I'm just going through it. I have run already. These are my results. Best mean square error 18.80. So let's do the feature importance analysis. Which feature has more importance after running the code? As we can see, 80 is the most important feature out of others. So this is a summary over here. So the results are here, and our conclusion is already there. The 80, the temperature, is the most important feature. So let's train our model, final model, with the optimal hyperparameters. After training this one, let's go for model evaluation to test the set, calculating mean square error and R square error. After running the code, we found MSE 19.39 and R squared 0.9340. Model evaluation results, as we just saw, is right here, given over here. Let's do the visualization of the residual analysis, which is given right over here. And as we know, our mean square in final square error is 19.39, or R squared is 0.93. So what is the conclusion? Our conclusion is the model has a very good fit, as demonstrated by the high R squared value of 0.9340, meaning that the random forest model explains over 93% of the variance in the PE, and MSE of the 19.39 is relative moderate suggested suggesting that the model predictions are reasonably close to the actual values, but there is still some error present that could be further minimized. Overall, the model performs well, and with possible tuning, feature engineering, or model refinement, the performance of the model might be improved even further. Thank you. Bye bye.